Okay, so to complete our plan of attack showing that NFA, DFAs, and regular expressions are equivalent, the only task left is to show how to convert an NFA into a regular expression. Because that would imply that NFA and regular expression are equivalent. We already saw that DFAs and NFA are equivalent, which means that all three are equivalent. And I'm going to do this. This is going to be a proof by example, which is not really a proof, but I want to just demonstrate the algorithm on an example, and the formal algorithm is not more complicated than that. You just have to formalize things, but I think you already suffered enough, and we're running out of time, so we're going to sketch this part. Okay, so the basic idea is that we're going to start with an NFA, and what we're going to do, we're going to convert it into a different style of NFA. It's a super NFA. It's like Superman but real. And the basic idea is that instead of having a transition function, which are characters or epsilon, which in the case of the regular NFA, now we're going to put on the edges, we're going to put regular expressions, right? And once we start in this process, the idea is now that we start removing states from this super NFA, rewriting it to an equivalent form. What we will get is edges with regular expression that get more and more complicated. But the number of states in this super NFA is going to be reduced until finally we will get an NFA that have a start state, an accept state, and a single transition between them, and this edge of transition would have a regular expression, which would be the regular expression that the original NFA accepts. So it's kind of magical. It's pretty in its own way. And it's easy. The nice also thing to say is that the algorithm is very clear once you look on an example, which hopefully, again, as I said, would be enough to see. Okay, so first we normalize the NFA. By normalizing, we add a special start state, which is distinct from the original start state. We add a special accept state, and we do an epsilon transition from all the accept state into this transition. So that's just the easy change. Okay, now we want to delete a state. In this case, we want to delete A. This is cancel culture brought you to NFAs. So how do we cancel A, right? So think about init, for example. Init state goes to A, but if A is no longer there, it can either go to B, right? And so it can either go with the character B to the state C, right? So we can just put directly an edge saying, go from init to C with the string B. Or alternatively, it can go to A, and from A it goes to, with the letter A, it goes to the state B. So we had a direct edge from init to B, right, with the label B. So far, so good. This is easy, right? We can really delete this state, and notice that the fact that we move the accept state to be an external state means that we don't have to worry about deleting accept state or any of these problems. Okay, so what's the next step? We redraw it, right? We no longer need the old edges and so on, so cleaner. And now we want to cancel B, right? So cancel B is going to be a bit more difficult if you think about it, because B has a self loop, right? Really, what's written here, if you think about B and the self loop, what this B really says is B star, right? It says you can repeat the self loop as many times as you want, right? So if I cancel B, if you go from init to B and from B to you travel to C, then you get the following regular expression, right? You get whatever is written here, which is A. Then you get whatever is written on the self loop of B, which in our case is B star, right? You get it, since it's a left loop, you get it with the cleanest star. And then you travel to C, you get A, right? So going from init to B can be skipped by putting it in this edge, which is this A, B star A, right? Okay. And now again, we want to do a cleanup. The only thing to observe is that now we have two edges that goes from init to C. One of them with B, one of them with this. But that's not the problem. We can merge them and just put an OR on the two regular expressions. So we get this, right? Now, oh, by the way, I didn't notice it, so that's why I went back. Notice that this edge AB, we converted it into A or B, right? So in fact, we now write on all the edges the regular expressions that corresponds to in this normalization process. But that's, you know, a minor comment. Okay? And now we just, you know, we have to cancel the state C, right? So we want to cancel C. So C again is easy, right? You, from init to get to AC, you have to travel on this edge. So this is the prefix. Concatenate with the self loop of C, which is A plus B star. And then whatever is in the edge between C and AC, which is epsilon, right? So you get this regular expression. This would be the regular expression for this edge. So we redraw it. And we get this. And now we are done, right? We get this super NFA that started the init, can match any regular expression, any string that matches this regular string and is accept. And since every step that we did not change the language that this super NFA accepts, we conclude that this is the regular expression that corresponds to the language, right? Now, you know, this was only an example, but hopefully after seeing this example, you can describe the full algorithm. It's not especially challenging. And that's it. So maybe before I finish, so what did we show? We showed that if I give you an NFA, we can translate it into an equivalent regular expression. We already saw the other direction, right? And we showed the equivalent from NFA to DFA. So now all three are equivalent, right? And regular expression, of course, equivalent to regular languages. So all the things are equivalent. And this is, you know, this is in some level very nice, right? Because we get these regular languages and we have these three different ways to think about them. And it's true that DFA, you know, and somehow it's kind of suspicious, right? Because DFA really look fundamentally different than NFAs. And DFAs and NFAs look fundamentally different than regular expressions. So it's somewhat surprising or, you know, nice that, in fact, no, those three things that look different are, in fact, the same. And this is it. Bye-bye.